Hello, everybody. How are you enjoying the Fling?
It's great.
Yeah, I'm glad you're enjoying it. This was a lot of fun to put on, and I'm really glad that I get to talk to you now about a really fun topic, dead trees. Yes, it is the time of the year where the big dark is upon us, so I'm going to confine the sad part of this talk to one slide. And here it is. Come on. Many trees are dying. That is considered bad. No, but really, there's a lot of people who think about sort of global change in forestry have noticed that there's a lot more mass tree die-off happening around the world. And we can see this confirmed through multiple data sources, both through remote sensing and people on the ground measuring stuff. We can see that that mechanism is primarily being driven by drought. However, there are some kind of local wrinkles in that trend. We can see that those droughts are getting more frequent and more intense, and we can see that forests are taking longer to recover following mass tree die-off. Okay, that was the sad part. Now it's gonna be a fun machine learning talk and kind of a human interest story about like how we track forest data. So there's two kind of main research questions that we can ask about this, and this is very closely related to what Nat was telling us about a little bit ago, so thank you, Nat, for setting this up. But two questions: where will mortality occur next? That's the forecasting aspect of this. And why does it occur there? Like I said, we know that drought is the main culprit, but what about specific species or topographic effects or all these other things that might be more relevant from the perspective of a local forest manager, a production timber operation, so on and so forth. And to really answer any of those questions, we first have to ask, well, how do we measure tree death? Spoiler alert, this is a machine learning talk, and yeah, you need data for that. Well, for doing this at sort of landscape scale, you really have two choices. You can send a satellite in space, have it take pictures, and look for dead trees in the pictures. There's a really lovely nonprofit called Global Forest Watch that spun out of the University of Maryland that does that. They're really cool. They have a great dashboard. But the thing about satellites is that their pixels are fairly coarse, and most operational products we have are like 10 to 30 meter pixels, or at least that die-off data is derived from those pixels. It's a little coarse. So the alternative to that is my personal favorite data set in existence, and that is you send people up in planes with iPads, you fly them around, and you have them draw blobs around the dead trees. I'm being serious. That program has existed in the US Forest Service since the 1940s is when the first time we did aerial surveys. And every year, almost every forested region in the country has a Cessna flown over it. And we've been doing that since about 1999 is when the data becomes like nationwide. So this is one of those polygons. I'm really glad we have a giant screen for this because I can ask you, do you see the dead trees?
They look mostly alive.
Yeah, they look pretty good, right? But they're in there. If you look really closely, you can see there's kind of, within that matrix of healthy green, there's some gray and some brown. This is the value add of aerial surveys. If you aggregated this NAPE image up to a satellite level, you wouldn't be able to see this. This is why the aerial survey program exists. But there's some problems with it. For one thing, a lot of those polygons that observers draw, they look a little funny. For example, this red line you're looking at, that's where the plane flew, and then all those multicolored patches, that's the mortality polygons. I don't know about you, I'm pretty sure trees don't die in nice, neat rows. And I'm pretty sure they don't die in shapes loosely approximated by a square. So that's one thing. Another thing we notice is that the amount of polygons you see depends on how far away from the plane you are. And you can imagine this is like, it's hard to look straight down out of the plane. It's hard to look really far away. But you can look in the middle distance pretty okay. And that shows up. You can see this signal. Hard part is they often don't publish the flight lines with this data. All the stuff with flight lines I'm showing you is from California in 2016 because that is the only time I was able to find flight lines. Most of the time, what we actually get is this gray background you're seeing of just like a loose survey area. You can clearly see that's just like a buffer around the flight line. But then when you also have the flight line, you notice things like this, where sometimes the flight line is perfectly aligned with the survey area. And then sometimes there's just a weird funky offset. And it's like, which one is correct? The flight line in this other data set or the survey polygon? That's a difference of like tens of kilometers there. That's kind of important. But we don't have the flight line, so we can't really ask that question in much detail. But alas, we recognize those problems. We can't really have a fix for them necessarily with the data we have available, so we just have to press on anyway and do our best to train a model. With this, we can ask two more refined questions of how do all those biases and issues in the survey data affect predictions? To do that, we can train one model based off aerial survey data and see how it does in comparison to one trained on those satellite-derived products that I mentioned to you before. And we also know just from the literature, and I mean honestly just basic intuition as well, that mortality dynamics are autocorrelated. And so how much does that autocorrelation matter in making these predictions? And to do that, we can compare models that are trained both with and without spatiotemporal context in the area in which they're doing predictions. So we're starting with a data in a polygon modality here, but for machine learning, we generally prefer to have things as pixels. So that's kind of the first step here is a rasterization process where we convert the survey area and the damage polygons to an image where each pixel is just either what percent of the forest canopy had mortality and no data if it was unsurveyed or not forest. And we can come up with some covariates for this. Again, Nat, I'm so glad you went right before me. This is perfect. Where we kind of split this into two categories of things that we think would ecologically be relevant to tree death. Things like weather, what trees are there, was there a fire there recently? As well as some sort of autocorrelation based things, which is just whatever mortality you had at the last time step, just feed that forward. And then whatever the maximum mortality was among neighboring cells, feed that forward as another covariate. But since we're doing forecasting here, a really great lesson I've learned about forecasting is that there's two easy, naive models you can come up with here that don't do any machine learning whatsoever. And that is, for a given observation, your prediction at time t is equal to the observation you had at the last time step. And then your prediction at t is the running average of all observations prior to that time point. So just to visualize what that looks like, this is a true mortality signal for an arbitrary pixel. I forget where exactly it is, but it's real, trust me. And you can kind of see how, last observation is just your data shifted forward one time step, and then the pixel average is kind of the running mean integrating over all that data. The key point here is that whatever forecasting model you come up with, regardless of what approach you use, it must beat naivety in order to be useful. So for the training setup on this, hey, we're doing cross-validation. That's another thing that Nat talked about. We're using gradient boosted machines for this. If you don't know what that is, it's a lot like random forest. If you don't know what random forest is, it's a model that's really good at regressing just kind of out of the box. The trick here is that we're evaluating the temporal generalizability of this. We're okay with overfitting to space, but we want to generalize across time. So the setup here is to identify 4 contiguous years of mortality data, train on that, and then validate on the following year. I have about 20 years of data in this project, so we have about 20 folds, and all the results I'm going to be showing you, each kind of like dot corresponds to one fold, like the summary of all performance along there. So let's look at some results. Starting with the aerial surveys, I want to explain a little bit about this plot. X-axis, normalized root mean square error. Smaller numbers mean a better model. Y-axis, those are the different approaches that we had. Those top 2 lines are the naive models. Then we have a GBM without spatiotemporal context, so without autocorrelation. And then a GBM with everything that we can fit into it. And this is based off the aerial survey data. The thing to notice here is that both of those naive models are doing pretty bad, and that's good. That implies that the machine learning approach we're taking is doing something. But the thing I really want to point out is that the gradient boosted machine without autocorrelation is doing no better than naivety. So that implies that all the environmental context that we know based off studies in greenhouses and very boots on the ground work that we know is related to mortality dynamics is apparently not predictive, at least based off the aerial surveys. And then naturally the model where you chuck all the data in does best. That's honestly not particularly surprising. Okay, so that's how it looks on the aerial surveys. What about Global Forest Watch? Well, here we get something a little bit different. If you notice that change in the scale on the x-axis, all these models are doing substantially worse than they did on the aerial surveys, but it's a very similar story like before. The 2 naive models are doing quite poor, and the GBMs are doing a little bit better, but adding those autocorrelation-based covariates seems to be really putting these models kind of over the edge to be the most competitive in this regard. The unique thing about Global Forest Watch, though, is that the GBM without autocorrelation covariates is doing slightly better than those naive benchmarks. And we can actually kind of make a map of what these predictions look like at a few representative areas in the Western US. And one thing I really want to highlight here is notice that in that left column, that's what was observed by the surveyors in 2022. And you can kind of see there's some artifacts. That's related to where the flight lines were. And then in the model output for the next subsequent year, it learns to draw those lines again. So those artifacts are kind of following into model predictions the next year. But when we remove spatiotemporal context, again, a GBM without autocorrelation covariates, those artifacts disappear. So although that right-hand map is based off like environmental context, I think that the main driver there is probably like tree species distribution. We know that it's not a very good prediction. And in fact, that one in the center column, even though it is not kind of following our intuition, it's not exactly useful to us from a management perspective. It's not useful for trying to understand why mortality happened. A kind of fundamental difference here with Global Forest Watch is you'll notice that pretty much all the pixels in this are dark purple. That's the big difference between aerial surveys and satellite-derived products. In satellite remote sensing, forest mortality has to be a massive die-off event. Everything in the pixel has to die for it to show up. And that's just not that's not the majority of mortality events. And so, yeah, we end up seeing like a sea of purple here and then a few pixels here and there that have a little bit of die-off. So the question I want to ask then is like dig into this aerial survey data set a little bit more. Why is it showing up like this? And this led me on a bit of a rabbit hole to look at the documentation for the aerial survey program, which by the way comes from the year 2000 and has not been updated since. Is one question you might be having in your head is like, are these surveys a snapshot of standing mortality or only recording new mortality, like new tree death that's appeared since the last survey? And based off their documentation, it appears to be the latter. At least that's what's stated. The surveyors are supposed to be only recording new mortality, but if we map out polygons, this is integrated over about 20 years of data near Lake Tahoe, there's a lot of overlap here. And these are color-coded by a severity attribute that's embedded in the polygons. So those bright orange ones are like 60% plus mortality in that area. And if you kind of sum up all these things, a lot of them go over 100% in a particular location. So is it a real true accounting of only new mortality, or is it repeat accounting of mortality that was seen last year and just happens to be reobserved again? We don't really know. And the real sort of lesson from all of this is that as with pretty much every other remote sensing product in existence, these aerial surveys need quality control. We know, based off of documentation provided from the Forest Service, that there are things like check flights and disputes about whether a polygon is real or not, but we, the end user, don't get to see that. It'd be nice to know, for example, if that giant purple polygon there was disputed, or if the people in the Cessna who were out there all agreed, yes, this is the true shape of this dynamic. We also know that the Forest Service conducts training flights where a bunch of people will fly over the same location, do a survey, and then they all compare notes. That would be a fantastic check sort of about the uncertainty of this data set. But those check flights are not made public. There is one paper from 2018 that flew their own survey that did a comparison between 4 observers, and that is the only existing public record of how consistent people are doing these surveys. And even then, I had to pester someone who was retired from the Forest Service to get those polygons instead of just like an image in a PDF. I don't want you all to sort of leave from this thinking that the Forest Service is doing a bad job though. This is really kind of an incredible piece of data that every single thing you see up there was hand-drawn. It's really worth kind of just reflecting on that for a moment. I find it kind of beautiful in its own way. And it can also be hard to think about what exactly it's like being up in a plane looking down at the ground for hours at a time, just from looking at QGIS screenshots like this. So I'll leave you, actually no, I have one more thing after this, but the second to last thing I'll leave you with is what it's actually like to be up in a plane. This is an animation I made in Google Earth Studio that roughly approximates the flight speed and altitude of the Cessnas that the Forest Service uses. And this follows a real flight line from 2016. As we move along here, you can get an idea of the sense of scale of some of these polygons. And you can imagine if I only have to manage a few of these at a time, it's pretty manageable. But then when you add all the surveyed polygons from that year, that's the extent of mortality that we're looking at and some of the places that are being surveyed right now. And it's frankly incredible that all of these things are able to be mapped, but then also in addition to that, each one of these polygons has an attributed host tree species that sustain mortality, the likely cause of that mortality event, and also the rough percent severity of how many of those trees were damaged in that particular mortality event. So this data set has a little bit of a ways to go before we can do impactful machine learning work with it, but I don't think that stops it from being an incredibly valuable look into our shared natural heritage. So I'll finish with what you model depends on what you measure. Aerial surveys, I've mentioned enough of that already. They lack some of the quality control that we need to really account for surveyor uncertainty and make great machine learning models from them. But if we remove that human element and aggregate up to the satellite level, those measurements are only capturing high severity mortality, but the vast majority of tree death is not high severity. So we limit ourselves if we only consider that source. So the way forward with this is to think hard about if we want to forecast mortality dynamics, the source of data we use for mortality is a key decision point. And if both of these sort of remote sensing derived approaches have key drawbacks, we might need to think about other ways of attacking this problem, like scaling plot level data. And so with that, thank you very much for listening. I'm happy to take any questions.
Yeah. Do you think, given the human factors biases in the hand-drawn polygon data, do you think it's a viable approach to use higher resolution imagery if it was available and have like quantitative classification methods, either to cross-check the humans or to supplement the data? I'm thinking about data sets like the National Agriculture Imagery Program.
Yeah. So the question was on can we use high resolution imagery to do automatic delineation of trees? Yes, that happens. It's very, very limited in extent though, because even things like NAPE are not quite high resolution enough for us to have not just accurate tree delineation, but accurate classification as alive or dead. And so you can imagine at the NAPE scale, one tree could be 3 or 4 pixels. And it turns out that there's considerable misclassification that happens at that spatial scale. So if we want to do automatic delineation, we need to go a step kind of above NAPE in terms of resolution. Yes?
I'm thinking an analogy in medical forensics where pathologists look at slides of biopsies, and I think it's fairly well known that well-trained machine learning and AI does better than a human. There's no fatigue. There's no bias. Well, there is bias certainly built into the machine, but and I'm wondering, can you envision something similar to the revolution that's happening in detection of cancers to something like treatment?
Yes. So the question was, is there an analogy here to the current revolution unfolding in the medical imaging community? And there is. In fact, one thing I'll plug is the website deadtrees.earth. That's a compilation of high-resolution drone imagery that has automatic segmentation. And so the real sort of challenge that I think we have to solve in understanding this problem is how do we take the high-resolution imagery of very limited spatiotemporal extent and generalize it to scales that are relevant to managers, or find a way to ingest just way more high-resolution imagery in order to do that, to make the delineation itself an operational data product. And I think we're at time. Thank you very much, everybody.